Hello everyone. My name is Shucheng Yi. I come from Beihang University in China. Today I want to share with you my exploration on accelerating convolutional neural networks training using sparsity. I will talk about my work mainly in three aspects: background, algorithm, and implementation. After that, I will show you the experiments and results, and make conclusion in the end. We all know that convolutional neural networks or CNN has become a powerful tool in many areas and performs very well in most of the computer vision problems such as detection, segmentation, face recognition, and Re-ID. However, CNN's training costs are huge and growing fast. How to make it possible to train CNN on budgeted computation platforms? Pruning is a widely adopted approach to accelerate CNN inference and has been widely studied. It can be divided into four categories: fine-grained, vector level, kernel level, and filter level pruning. Different from pruning of inference, it is challenging to take advantage of sparsity in training procedure. Pruning of inference can be split in two stages: pruning stage and inference stage. Pruning cost will not introduce additional inference runtime. However, in pruning of training, pruning cost will influence the training time, model accuracy, and convergence. More specifically, there are three main challenges to accelerate CNN training by pruning: how to select the elements to be pruned without using too much resources, how to protect convergence and accuracy of origin model, and how to utilize the sparsity brought by pruning to accelerate CNN training. So we propose a series of methods to solve these problems. Firstly, let me briefly introduce the training process of CNN. CNN training contains two stages: forward and backward. Backward stage can be split into two steps: activation gradients back-propagation, and weight gradients computation. Our pruning target is the activation gradients which participate in most calculations of CNN backward propagation. For the first challenge, we proposed a distribution-based threshold determination method. According to our observation and previous works, we assume activation gradients subject to a normal distribution with mean value 0 and variance sigma square. We can use the mean value of the absolute values of gradient data to compute the unbiased estimator of sigma. With the cumulative distribution function of the standard normal distribution phi, target pruning rate p, and the estimator of sigma, we can calculate the pruning threshold tau. The gradients whose absolute value is under the tau will be pruned. For the second challenge, we adopt stochastic pruning rather than direct pruning to alleviate accuracy loss. In L. Batu's GOGA General Online Gradient Algorithm framework, there are two important assumptions for convergence. Correspondingly, we propose a stochastic pruning algorithm which has two key ideas. Maintain the mathematical expectation of the gradients and only generate limited noise. Our pruning method will maintain the gradients larger than threshold and set the gradients under the threshold to 0 or ± tau according to its absolute value. And here is the pruning effect. We provide a mathematical analysis why applying this gradient sparsification method to a convolutional neural network during training does not affect its convergence. Next, I will show you our implementation to utilize the sparsity of activation gradients to accelerate CNN training. The first problem of implementation is where to prune. Modern CNN models has two typical structures, conv-ReLU and conv-BN-ReLU. In backward propagation, batch norm will introduce non-sparsity, and ReLU layer can inherit sparsity. So in conva-ReLU structure, we put the pruning layer after the ReLU layer. In conva-BN-ReLU structure, we put the pruning layer before the batchnorm layer. Pruning layer is a straight-through estimator which can be defined as most modern deep learning frameworks including CAFE convert convolution into matrix multiplication by applying the combination of image to column and column to image functions. The former turns a 3D feature map tensor into a 2D matrix by data reuse, and the latter is the inverse function of image to column. So the acceleration of training with sparse activation gradients can be accomplished by replacing the original matrix multiplication with sparse matrix multiplication. We found that dense and sparse matrix multiplication is needed for AGBP step. However, the existing BLAS library such as Intel MKL only support multiplication between sparse matrix and dense matrix. So we need to transpose weight and activation gradient in this step. To save the computation time, we change the origin image to column and column to image functions so we can get transposed matrix after calling these functions. The modified calculation procedure can be summarized as. In this section, I will introduce results by following several aspects: accuracy, sparsity, convergence rate and speedup rate. Our pruning approach is evaluated on AlexNet and ResNet 18, 34, 50, 101, 152 with CIFAR 10, CIFAR 100 and ImageNet datasets. As we can see, the accuracy loss is almost negligible when a non-aggressive policy is adopted for gradients pruning. Meanwhile, it can raise the sparsity significantly. Our pruning method doesn't have significant effect the convergence rate in most cases. This conclusion accords with the our convergence analysis. It means that our pruning algorithm can not only accelerate single training iteration but also the whole training process. Our proposed training scheme is evaluated both on Intel CPU and ARM CPU platforms, which could achieve 1.71 times to 3.99 times, and 1.79 times to 5.92 times speedups, respectively, when compared with no pruning utilized at back-propagation stage. Compared to existing works, our work have better speedup rate and accuracy. Moreover, our work is also well performed on ImageNet, which is more challenging but has not been evaluated in existing works. As a conclusion, in this work, a stochastic pruning algorithm is proposed to utilize the sparsity in CNN training. We also designed a distribution-based threshold determination (DBTD) method to compute the pruning threshold. Theoretical analysis is provided to guarantee the convergence. Besides, evaluations on state-of-the-art models have confirmed that our gradients pruning approach could accelerate the back-propagation up to 3.99 times on desktop CPU and 5.92 times on ARM CPU with a negligible accuracy loss. Thanks for your listening.